Hello and welcome everyone. Today we will talk about our project one. My name is Faisal Masmoon.
Hi, I'm Emiliano Ramirez.
I'm Ian Mullins.
In our project one, we will talk about few things, and just to help you guys understand what we will talk about, we will talk about explanation for the project and the understanding of how does it work, all the calculations that we know and we figured out, and we will add some sense making just to connect everything together and the conclusion, and at the end, short reflection. Explanation. When we rotate the table, the object on the table is pushed away, and that's because it's connected to another mass. And at the same time, it's rotating. The mass it's connected to is we would like to call it M capital or M2, and it's below the table. And the only thing connected between both of these are a rope that goes through the center of the table. When we rotate the table, the object on the top of the table wanna be pushed away. But at the same time, when that happens, the object below the table wanna go up. And we wanna try to figure out where's the sweet spot where we can keep rotating the table and the mass below the table will stay still, which means it's not going up or down. And that's a short video demonstration of how does this experiment work, similar to it. In this video, Robin case is basically rotating the rope for the object above the table, or supposed to be above the table, in different speeds, and we can see that the object below the table is going up. The faster he goes, the faster it's gonna go up. The slower he goes, it will fall down. Thank you.
All right, so I'm going to start by going over a few things this problem gave us and what this problem is really asking us to find. So I have to find a few variables to distinct between my big box M and the small ball. And we made a few assumptions and a few things were given to us in the problem statement, but our string is ideal, our pulley is massless, and we have a frictionless turntable. I'm also going to assume that the force of gravity is 10 and that we're close to the surface of the earth for this problem. And what this question is kind of trying to ask us is, what is omega, so that the box M doesn't either pull in or fall off of our turntable. And how we're going to find that is using Newton's third law. Because we have a massless pulley and ideal string, we can say that the force of tension applied to our big box M equals the force of tension on our small ball. And we're going to solve for that using torques and friction. So I summed up two different torque equations here for our small ball. I used torque equals R cross F, and I simplified that to RF sine theta, and that simplified more to RF because our angle here is 90 degrees. I also wanted to relate this to the acceleration, the force applied by the force of gravity on the ball. So I made a torque equation for I alpha on the ball as well. And the I of a hollow sphere is 2/3 mr squared. On this slide, I found that acceleration on the ball by comparing the force of gravity to the force of tension on the ball. And then with all that information, plugged it back into my T equations for torque and set them equal to each other so that I could solve for the force of tension, and that ended up equaling 2/5 the force of gravity. Okay, so then centripetal acceleration is that force we're going to be looking for with the force of tension on our big box M, and that is equal to V squared over R, and I can rewrite that as omega squared R squared over R, simplified to omega squared R. And then I'm going to make a Newton's second law, F equals ma for the block, And the force is just the force of tension we found earlier, big M, and that centripetal acceleration that I just solved for as omega squared r. I'm going to simplify all that and eventually find that omega equals the square root of 2/5 mg over big M, big R. And if we're going to look at units here for a little sense making, going through all of it, I get per second, which is perfect because radians are unitless in a linear system. And thinking about what each piece here tells us, it makes sense that as the small m and the force of gravity are working to increase the centripetal acceleration, our omega is going to have to go faster to work against that. Or vice versa, as our big M and big R increase, omega is not going to be nearly as big or have to be as big to counteract that force from the ball.
Alrighty, so I'm gonna go into a little bit of a reflection. So of course we didn't solve this problem out of nothing, right? We have to build some knowledge, building blocks, if you will. For the next few slides, I'm gonna be talking about some problems that we've seen in the past that kind of gave us some base knowledge into how to basically solve this problem. So homework activity that we've seen is homework 3, activity 3. It's a massive pulley, and essentially you've got a table with a massive block on top and then a smaller block hanging off the side of the table with a pulley attached there. Basically, you deal with a lot of torques there and you need to find the force. But of course, it doesn't have a rotating table, so that's the main difference, but it still allowed us to kind of understand what was happening between the two blocks and the pulley in that system. And then we've also seen an example in Studio 3, Activity 1. This was just the pulley with two blocks hanging off from it, no table at all in this case. But we were allowed to look at the torque and what was going on with those two blocks and seeing what kind of went into that equation and seeing what happened. And that about wraps up our project 1. Thank you all for watching. Bye.
That was beautiful.